You're listening to the Science of Everything podcast, episode 61, Magnetism, and I'm your host, James Fodor. In this episode, we're going to look at magnets, magnetic fields, magnetic poles, electromagnets, basically all the core concepts of magnetism. We're going to look at how they work and why magnetic forces are caused. So we'll talk about the different types of magnetic materials responsible for that, so ferromagnets, paramagnets, and diamagnets. I'll also talk about some applications of magnetism, including electric motors and generators, and I'll end with a brief discussion of Maxwell's equations. Recommended pre-listening for this podcast is episode 43, Electric Fields and Forces. Okay, let's get started. First of all, to introduce magnets and magnetism. So what are magnets? Probably everyone who's listening to this has played with magnets before. They're quite fascinating things, and as far back as the ancient Greeks, I think even earlier than that, we have records of them uncovering and using a material called lodestone, which is a form of iron oxide. And it's a naturally occurring mineral. Well, all minerals are naturally occurring, but anyway, it's a naturally occurring rock which attracts pieces of iron, so it's naturally magnetized. It's, as far as I know, the only real example of a mineral like that, which just in its natural form is strongly magnetic. It turns out that you can actually transfer this magnetic property to pieces of iron and some other metals. So if you rub iron, like a small iron nail or whatever, with a lodestone, it will become magnetized, and then you can take that magnetized piece of iron and use it to attract other pieces of iron. So you can transfer the magnetism to other pieces of metal. So this fascinated the ancient Greeks and peoples throughout history, as far as I understand. Only recently have we been able to explain scientifically what's going on here, because it seems a very mysterious force, magnetism. It acts at a distance. You try to push two magnets, the north and the south pole together, two north poles together, and they push apart from each other. No matter how hard you try, if the magnet's strong enough, you can't actually get them to touch. It's this very strange force that acts at a distance. At least it's intuitively strange to us, because it's not the sort of thing we're used to. So what causes this strange phenomenon? Well, magnetism, broadly speaking generally, refers to the class of physical phenomena that relates to the forces exerted by magnets on other magnets. And a magnet itself is just a material or an object which produces a magnetic field. The magnetic field itself is invisible, although you can try and visualize it by various means, for example using iron filings, which are just small pieces of iron which will line up along a magnetic field if placed close enough to it. So you've probably seen that in a science class or video somewhere, iron filings being used to show a magnetic field. But the magnetic field itself is invisible, and it's only the iron filings that you're seeing. But the field is what's responsible for the force. It pulls or pushes on other magnetic materials, and so causes movement, causes the force to be exerted. But what is a magnetic field? Well, if you recall from episode 43, or maybe other episodes where I've talked about electricity, a magnetic field is similar to an electric field. It's basically just a region of space, but it's a region of space that we describe mathematically as exerting a force, the force being proportional to the size of the strength of the field at that location. So the magnetic field is a mathematical description to describe the magnetic influence of electric currents and magnetic materials on other electric currents and magnetic materials. So at any given point in space, the magnetic field is given both a direction and a magnitude. So that means it's a vector. It's an arrow that has a magnitude and points in a particular direction. And it's measured in units of Tesla. Magnetic field lines, which comprise the magnetic field, so usually when you draw a magnetic field, you draw it in terms of lines. The lines always begin at a north pole and end at a south pole, so they usually have arrows on them that point towards the south pole, and they sort of curve around outwards. Again, you've almost certainly seen these diagrams of magnets with the magnetic field lines, with the arrows pointing from the north pole towards the south pole. The arrow represents the direction that a north pole will tend to align if placed in that field. So bar magnets, if you place them in a magnetic field, would tend to align so that they were lengthwise along the field, with their north poles facing in the direction that the arrows point, that is, facing towards the south pole. So I've been talking about magnetic poles. What is that exactly? Well, magnetic poles are sort of analogous to electric charges. In electricity we have positive and negative charges, and they attract each other. So unlike charges attract, like charges repel. Well, it's similar in magnetism. Like poles repel and unlike poles attract. So the north pole attracts the south pole, but two north poles will repel each other. That's why the north pole of your bar magnet will align itself so that it's pointing in the direction of the arrow, which in turn points in the direction of the South Pole, because the North Pole it tends to move, is attracted to the South Pole. Now, there's one very important difference, however, between electric charges and magnetic poles, and that's why they're called poles, sort of analogous to quite analogous to the North and South Pole of the Earth, in that you always have two magnetic poles. That is, if you take a bar magnet and cut it in half, you get two smaller bar magnets, each with a new north and south pole on one and a new north and south pole on the other. If you cut those in half again, the same thing happens. You'll have four bar magnets. So this is very different from electric charge. If I have a piece of matter which is positively charged on one side and negatively charged on the other side, and I cut it in the middle, then all I'll have is two pieces of matter, one which is positively charged and one which is negatively charged. But that's not what happens with magnets. You cut it in half, you get two smaller magnets. You don't get one north pole and one south pole. So this is what we call a magnetic dipole. Magnets are always dipoles. That is, they always have a north and a south pole together. And it doesn't matter how small you try and make them, even to the atomic or subatomic scale, we have never yet discovered a magnetic monopole. It's thought that they might exist, but they're certainly not common or easy to find. A lone north pole or a lone south pole. Maybe some exotic type of matter that we don't know of would exhibit a magnetic monopole. But as far as we know, magnetic monopoles don't exist. And so, for all practical purposes, we can say that you always have a north pole and a south pole together in a dipole relationship. Okay, so that's some basics on magnets and magnetic fields and magnetic poles. Let's now talk about the relationship between electricity and magnetism, because as we'll see that they're very closely related. So first I want to talk about the Lorentz force law. Now this might sound a bit complicated, but basically all it is, it's an equation which describes how a charged particle, or specifically a moving charged particle, that is an electrically charged particle like a proton or an electron, how that is affected by a magnetic field. If you let's just go back to the electric field case for starters, because that's the simpler case. If I put an electron in an electric field, well, let's say I put a positive charge in a proton in the electric field, just to make things a bit easier. What will happen is that proton will, a force will be exerted on that proton, and it will begin to move in the direction of the electric field. So it moves along the electric field lines. So the electric field lines point in the direction of the force that acts on the proton, and thus the proton moves in that direction. It's fairly simple. However, with magnetic fields, it's much more complicated. If I put that same proton in a magnetic field, well, first of all, if the proton is stationary, if it's just sitting there, actually nothing will happen at all. It turns out that charged particles in a magnetic field, if they're stationary, so stationary charged particles in a magnetic field, don't experience a force. Nothing happens. They only begin to experience a force if they are moving. So a moving charged particle placed in a magnetic field experiences a force as a result of that field. That is, the field exerts a force on the moving charged particle, but a stationary charged particle does not. It has to be charged as well. If I put a moving non-charged particle in a magnetic field, that doesn't do anything either. So it has to be moving and it has to be charged. But it's not just the motion, it's the direction of motion that matters as well, because the charged particle actually has to be moving perpendicular to the direction of the magnetic field. If it's not moving perpendicularly to the field, then only the vector component of its motion that is perpendicular to the field will contribute to the force. So that is, if you imagine a proton that's moving sort of diagonally relative to the field, you could imagine splitting up that diagonal motion into some up motion and some sideways motion. Imagine the magnetic field is going sideways and the proton is moving diagonally. Now, instead of moving diagonally, let's imagine that the proton is moving partly upwards and partly sideways, because in fact that's just a different way of saying diagonally, like it's a vector decomposition of its diagonal motion into some up motion and some across motion. So only the upward part of the motion, the upward part of the diagonal motion, that's called the vector component of the motion of the proton that's going upwards, will actually contribute to the force that's exerted on the proton by the magnetic field, because only the upwards component of the velocity of the proton is perpendicular to the magnetic field. The part of the velocity of the proton that is parallel to the magnetic field has no effect. So that means even if a proton was moving, but if it was moving just in the direction of the magnetic field, then the magnetic field would not exert any force on the proton at all. The force would be zero. So magnetic fields only exert forces on charged particles that are moving perpendicular to the field, or they only exert a force proportional to the vector component of the motion of the charged particle that is perpendicular to the field. I'm afraid this is hard to explain without diagrams, but I will put some up on the Facebook page, so by all means go and check those out there if you're having trouble following what I'm saying. But unfortunately, it gets even more complicated, because a magnetic field does not exert a force in the direction of the magnetic field. It exerts a force perpendicular to the magnetic field. So, let me try and explain this. Let's go back to our case of the electric field. Remember the nice simple electric field? In an electric field, it doesn't matter where the proton is moving. The force is just proportional to the strength of the field and the charge of the proton, but that's all. Also, the force always acts in the direction of the field. Nice and simple. In a magnetic field, it's completely different. As I said before, a stationary charged particle doesn't experience any force because of a magnetic field. Only one that's moving perpendicular to the field will experience a force. But further, there's an extra complication, because the direction of the force is actually perpendicular to both the direction of the velocity of the proton and also the magnetic field itself. So we've got three vectors which are all perpendicular to each other. So if we imagine the magnetic field pointing away from you, directly in front of you and away from you, if the magnetic field's pointing that way, suppose that your proton was moving to the left. It was moving from right to left in front of you, so towards the left. If that was the case, so we've got a proton, which is a charged particle, and it's moving perpendicular to the magnetic field, so that means it's going to experience a force from the magnetic field. But here's the question: which direction does the force act in? Answer is that it does not act. The force doesn't act in the direction that the proton is traveling. It doesn't act from right to left, as you might expect it. Instead, the force acts upwards. So remember, our situation is the magnetic field faces away from you. The proton is moving from right to left. That means the force acts upward. You'll notice if you sort of consider these arrows, one pointing away from you, one pointing to the left, and one pointing up, they're all perpendicular to each other. Each one is in a different dimension. So the magnetic field is perpendicular to the velocity of the proton, which in turn is perpendicular to both of, and the force is perpendicular to both the velocity of the proton and the magnetic field. So this very strange relationship of everything being perpendicular to everything else means that if you put a charged particle in a magnetic field, and the particle is traveling exactly perpendicular to the field, it will move in circles. It'll basically do an orbit about one point of the field. And you can easily show this, because the direction that the force acts in keeps changing as the direction of motion of the proton changes. So it's very simple. It's basically the magnetic force acts as a centripetal force, a center pulling force. If you can't see why that would be the case, just take a look at a diagram. As soon as you see an animation of it, it's immediately obvious why this is the case. But it's a very strange phenomenon that if you put a charged particle in a constant magnetic field, and that the particle is traveling perpendicular to the field, then it will travel in a perfect circle, just around and around and around forever, as long as that setup it remains the same. So a very different behavior to if we put that same charged particle in an electric field. So that's all of that complicated behavior is described by the Lorentz force law. So hopefully it was somewhat clear. Remember, the main point is that the velocity of the direction of motion of the charged particle, the direction of the force, and the direction of the magnetic field are all perpendicular to each other. They all point in different directions. Okay, so I've just been explaining how charged particles are influenced by magnetic fields. But I started off the episode talking about lodestones and magnets. So how are these two related? How are lodestones and bar magnets related to electric charges? Because we seem to be talking about different things here. But as it turns out, electricity and magnetism are really just two sides of the same coin. They're actually essentially the same thing, or very slightly different versions of the same thing. Now, exactly how does that work? Well, it works in two ways. First of all, as I've already explained, magnetic fields exert a force on moving electric charges. So that was what I was just talking about with the Lorentz force law. Magnetic field, moving charge, the magnetic field exerts a force on the moving charge. But it turns out it actually works the other way as well. So not only do moving charges experience a force from magnetic fields, but moving electric charges actually generate a magnetic field as well. So if I put a proton in a magnetic field, not only will the electron feel a force from that magnetic field, but the electron, as it moves, will also generate a magnetic field of its own. A somewhat more general way of saying that, which relates to Maxwell's equations, which we'll come to in a moment, is that a changing magnetic field produces a constant electric field, and a changing electric field produces a constant magnetic field. So we've got these two fields, electric fields and magnetic fields, and if you change one of them, that is if you change its magnitude or direction, then in the same space, like in the same region, volume of space, you will also generate the other type of field. So this is a sort of a self-perpetuating process, because if I start out with an electric field, and then I change its strength, I increase its strength, say, well, I've changed the electric field, so that means I'll produce a magnetic field. But the magnetic field doesn't just pop into existence out of nowhere. If I'm slowly changing the electric field, then I'll slowly get a forming magnetic field. But now I've got a changing magnetic field as that magnetic field comes into being, so I'll also change my electric field. And because I've got a changing electric field, I'll also get a changing magnetic field. And so the two feed off of each other. And this is essentially what happens when we have electromagnetic radiation. You may have heard that electromagnetic radiation is essentially just electric fields and magnetic fields, and they're perpendicular to each other, and they're constantly oscillating. That's all it is. It's because changing magnetic fields produce electric fields, and changing electric fields produce magnetic fields. The two are very much related to each other. In fact, if we jump a bit beyond this episode now, but just to whet your appetite for future episodes or future reading that you can do yourself, if we go into the realm of special relativity, it actually turns out that whether a given phenomenon is an electric field or whether it's a magnetic field depends on your frame of reference. So one person might look and say, well, this is an electric field. Another person might say, if they're moving at a different velocity or they have it, they're in a different frame of reference, they might say that it's a magnetic field. So there's no actual intrinsic difference between electric and magnetic fields. It kind of all depends on your perspective. Anyway, back to the main topic of the episode. So just to consolidate this notion of the very close relationship between electricity and magnetism, that means if I have a loop of wire, and if I move a magnet towards it, then a current will flow through the wire. If I move a magnet away from the loop of wire, a current will flow through the wire in the opposite direction. If I have two wires next to each other and I flow a current through each of them, then there is actually a force exerted between the wires. If the currents flow in the same direction, the wires will be attracted to each other by the magnetic force, and if I flow current in the opposite directions in each wire, then they're pushed apart. That's because each wire, the current through each wire is a changing electric field, which in turn produces a magnetic field. If the currents are in the same direction, they produce essentially the same magnetic field, which attracts the wires to each other, but if the currents flow in the opposite directions, then the magnetic fields repel each other. Another manifestation of the relationship between electricity and magnetism is what's called an electromagnet. You may have heard this term before. An electromagnet is a magnet that's produced by an electric current. And making an electromagnet is very easy. All you have to do is wrap a wire in a coil around usually an iron rod or other piece of metal. And then you run an electric current through the wire. And the result of that is that the magnetic fields are well, obviously a magnetic field is produced because we're running electric current through the wire. That means there's a changing electric field, which means we're going to produce a magnetic field. But particularly, the coil arrangement of the wires produces a field in exactly the same shape as if there was a bar magnet. So in other words, if I have an electromagnet with, a coil of wire wrapped around, say, a non-magnetic piece of iron, or it even could be a piece of plastic. I mean, it wouldn't work quite as well with plastic, but you could do it with plastic. So if I wrap wire around a piece of plastic, if I coil it around, then if I hold that in one hand, and then I hold a bar magnet in the other hand, and, they're roughly the same strength, they'll behave exactly the same way. They'll both be magnets in just the same way. I won't really be able to tell which one is which unless I looked at them, but their behavior is essentially the same if I make them the same strength. So an electromagnet, it behaves just like a bar magnet. So pretty cool. And electromagnets are particularly useful because unlike sort of regular bar magnets, you can turn them on and off at will and vary their strength as much as you like by just changing the current. You could even change the polarity, flip around north and south poles just by changing the direction that the current's flowing in. So very useful things, electromagnets. They're used a lot in industry and science. Okay, so I've talked a lot about the relationship between electricity and magnetism and the way that electric charges interact with magnetic fields and things like that. But I still haven't explained exactly where this strange force comes from. Exactly why is it that a moving electric charge has a force exerted on it by a magnetic field, and where does this magnetic field come from anyway? I mean, I've said that it represents a force, but where does it come from, and why are some things magnetic and other things not magnetic? So we all know, that if I try and put a magnet on the fridge, then that works fine, it stays there. But if I try and stick my pen to the fridge, it just falls off. Some things are magnetic and some things aren't. Well, why is that? Similarly, if I have a magnet, I can stick that to my metal fridge, but I can't stick it to my clothes or to a wooden chair. Magnets only attract certain materials. So what's with that? So this leads us on to the topic of magnetic materials. Before we talk about the different types of magnetic materials, I will need to explain exactly where the force of the magnetic force comes from. And this is a little bit tricky, so bear with me and we'll see how well I can explain this. The fact that electric currents and magnetic forces are very closely related allows us to understand that the ultimate source of magnetism is actually just always moving charges. That is, all magnetic fields come from moving charges. Now, those can be sort of macroscopic in a sense, like an electromagnet. I know that it's a moving charge because I've got a big wire that's got current flowing through it. That's an obvious case where where the magnetic field is caused by moving current. But in fact, all other magnets, even the bar magnet, the regular bar magnet of iron that I pick up and use with the iron filings, even the magnetism of that is actually the result of tiny moving currents. But in this case, it's sort of at the subatomic level. A simple way of thinking about it, which isn't really correct, but it might help, is that magnetic fields are always caused by moving charges moving around. And that at the atomic level, we have electrons moving around in orbits about the atoms. But electrons are charged, of course, they're negatively charged, and so as they move about the atoms, they're an electric charge in motion. They generate a magnetic field. So any material that has moving electrons will generate a magnetic field in that way. Now, that's the simple way of explaining it, but it's not actually correct. But it's a helpful way of thinking about it because it's kind of correct. So if you understand that, that's a good start. I'm now going to explain, at least try and explain a little bit more correctly what's actually going on. But if you don't follow this next bit, then just focus on what I said first, because that's sort of close enough. But it's not actually the case that electrons are moving around the atomic nuclei in sort of circles like that. We know that electrons aren't actually particles that move in classical motions like that. They're probability distributions that are smeared over space. And so it doesn't really work to think of them as moving particles which generate a magnetic field in the same way as an electric current does. In fact, electrons have a special property called intrinsic angular momentum, or spin, it's also called. You might have heard spin up and spin down electrons. Well, that's what it's referring to. Electrons can either be spin up or spin down. It's not really very helpful to ask what is spin, because it doesn't have really any classical analog. That is, there's nothing in the real world that we can point to and say, well, spin is that thing, or it's like this. It's not really like anything. The closest thing it is to is like if you're whirling an object around your head, like a rope or whatever, and you feel a force pulling it away from you in a sense. You have to pull inwards to keep it going around you. Well, that's a centrifugal a centripetal force. You're pulling it in because it has angular momentum. The spinning motion of the object around you has angular momentum, and it will tend to continue in the direction that it's traveling. That's the closest analog we have. Now, the thing about an electron is that it's not really spinning. It's not like they're little tops. Electrons are point particles as far as we understand them, and they're also probability waves. They're a bunch of things. So nothing is really spinning, nothing is really orbiting anything else. The electrons just exist in various probability fields or distributions around the nuclei of an atom, and it turns out that they have a property which behaves like angular momentum, but it's not produced in the same way as angular momentum. It's not produced by anything literally spinning. It just behaves that way. So that's why we call it spin or intrinsic angular momentum, but it's got nothing to do with anything actually spinning as far as we know. Now, as I mentioned before, electrons can have either spin up or spin down. If maybe an atom has 6 electrons, if 3 of them are spin up and 3 of them are spin down, then the spins cancel out and there's no net spin, there's no net intrinsic angular momentum to the atom as a whole. However, if the spins don't cancel out because you have some unpaired electrons, then the atom as a whole has some net spin in a sense, and that is what generates the what we call the intrinsic magnetic moment, which is basically the analog of the magnetic field that is produced by a classical moving charged particle. So let me try and say that again. If I have a classical particle, just Forgetting quantum mechanics, just an ordinary electron, obeying the laws of classical mechanics, and it moves around. It's a moving charge, so it generates a magnetic field. Particularly if I imagine it going around in a circle. It's moving around in a circle, so it generates a magnetic field. If it was moving around in a circle, it would have some angular momentum. That's where you get angular momentum, circular motion. Okay, so that was our classical world. Now let's move to the actual world, the quantum world. In the quantum world, it turns out that electrons have angular momentum, even if they're not moving, even if they're just sort of there in the atom. Because they're not really moving, they're not orbiting the atom. That's a wrong way of picturing it. Even if the electron was just sitting still, which it can't really do, but even if it sort of was, it still has intrinsic angular momentum. And because it has intrinsic angular momentum, it also has some intrinsic magnetic moment. So it's like the electron is orbiting the atom, and thereby generating a magnetic field or magnetic moment, even though it's not actually doing that in a literal sense, but it behaves like it's doing that, which is why it's sort of okay to tell the story that I said at the start, which is that the electron is orbiting the atom, and as it moves around, it's charged in motion, thereby it generates a magnetic field. That's why it's kind of okay to say that, because it behaves like it's doing that, even though it actually isn't. It just has this intrinsic property of magnetic moment, which generates a small amount of magnetic charge. Obviously, each electron doesn't generate very much of a magnetic field by itself. It's when you put lots of them together that they can generate a large magnetic field. Now, I mentioned before that if the electron spins, or angular momenta, cancel out, then the object as a whole, or the material as a whole, does not exhibit any magnetic behavior. And most materials are like that. Most materials are such that the spins roughly cancel each other out, and so you don't have any net magnetic behavior for the material as a whole. But some materials, because of particularities relating to the atomic structure of the material and also the molecular structure of the way the ions are arranged in lattice, there's a lot of complicated aspects that determine exactly the magnetic properties of a material. But suffice it to say, for complicated reasons, some materials have unpaired electrons which are able to align with each other and produce, thereby, instead of cancelling each other out, the magnetic moments of the electrons add up and reinforce each other. And so the material as a whole produces a magnetic field. And this is exactly what a bar magnet is doing. Well, first of all, the iron has unpaired electrons. That's essential. Unpaired just means that there are some spin-ups that don't have spin-down partners, or vice versa. So there's some left over to produce a net magnetic field. But having unpaired electrons by itself isn't enough, because they also need to be aligned. If for every unpaired spin-up electron in one atom, you have an unpaired spin-down in a different atom, then again, they still cancel each other out. It's just in different atoms this time, instead of inside the same atom. So unpaired electrons isn't enough. They also need to be aligned across the different atoms. And this is where iron and some other metals are special, because they are able to do this. They line up their magnetic moments across the different atoms. Thereby, they add up and produce a macroscopic magnetic field that we can detect and use. And so this is what a bar magnet is doing. It's the magnetic field in total is produced by the combination of all of the tiny contributions of each of the electrons in the metal. And that's where the magnetic field comes from ultimately. It's the electrons. Now, I need to explain a couple of other points, because I've been talking about iron being this material that has unpaired electrons and in which the electron spins can align so that you get a macroscopic force. But then why isn't every piece of iron magnetic? If it's the material that has this property, then why isn't every bit of iron that we interact with magnetic? That's obviously not the case. In fact, only some pieces of iron are magnetic. You have to do something to iron to make it magnetic. Well, what is it that you have to do to it? Well, there's an extra complication here. This is it relates to what are called magnetic domains. So, to explain this, I first need to explain what a ferromagnet is. So, a ferromagnet, that's iron. Iron is a ferromagnet. In fact, it's the main one that we talk about. There are some others as well. I think cobalt and nickel are ferromagnets as well, or can be. But think of iron when you think about ferromagnets, because ferromagnets are materials that exhibit strong macroscopic magnetic behaviors. Most materials are not ferromagnets. So wood is not a ferromagnet, plastic is not, but iron is. So iron has unpaired electrons, so ferromagnets must have unpaired electrons, and also ferromagnets must have a way for these unpaired electrons the spins of these unpaired electrons to align with each other across large spans of the material, so that they don't all cancel out, so that you can get a field, a macroscopic field. So that's a ferromagnet. However, there's an additional complication, because in order to exhibit macroscopic magnetic behavior, ferromagnets must also have all of their magnetic domains, or at least most of them, aligned with each other. Now, what do I mean by this? Well, a domain is basically like a portion of a crystal lattice. So imagine if I have a lump of iron here. Iron is a ferromagnet. So why is this lump of iron not attracting these iron filings over here? Well, because this lump of iron is obviously it's not acting as a magnet, but why not? It's a ferromagnet, right? It has unpaired electrons. The spins can line up with each other. So why is it not acting as a magnet? Well, the reason is because if I zoomed in to this lump of iron, I would see that it's not a single crystal lattice. It's actually composed of many smaller subsections of crystal lattices. You can sort of imagine this as different blocks of ice that are frozen separately and then clumped together. The blocks of ice are connected and they might be tightly packed, but they're still sort of separate from each other. So the crystal structures in the different domains are separate from each other. And in particular, within each domain, the spins of the electrons might be aligned with each other. So maybe in this domain, the spins are all pointing to the left. But next to it, there's a different domain where they're all pointing to the right. And then below that, there's a different domain where they're all pointing up. And these domains might consist of, thousands or millions or billions of atoms, but they're still quite small by our standards. So this given lump of iron might have, many, many domains inside it. Each domain in turn having many electrons inside it. So each domain might have, the atoms in that domain might all be aligned so that their electron spins are all in the same direction. But because the domains are all pointing in different directions relative to each other, the lump of iron as a whole is not magnetic, or at least it does not exhibit macroscopic magnetic properties, because the domains are all out of alignment. So it's not enough to have your electron spins all aligned with each other. You also have to have all your domains aligned with each other. Only when you have both of those things at the same time do you get a magnet. So that's why every piece of iron is not magnetic. You can make pretty much every piece of iron magnetic. I mean, it does depend on some other factors as well, but basically every piece of iron is potentially magnetic, but you have to align the domains properly. How do you do that? Well, an easy way to do it is to put a piece of iron inside a magnetic field and then heat it up a little bit or shake it or strike it or do something like that, basically to move around the domains. The domains, given some force, will tend to align themselves along the magnetic field lines. Then if you take that piece of iron out of the magnetic field, the domains should stay in alignment, and so it will stay magnetized. If you heat it up to a high enough temperature called the Curie point, then random thermal motions will scramble the domains again. Also, if you drop it, the domains may lose their alignment as well. So if I have a piece of iron, that's a ferromagnet, remember the magnetic type of materials. Say that it's the domains are all scrambled, so it's not a magnet. If I put it inside a magnetic field and maybe stroke it with a magnet or just whack it a couple of times, whatever, the domains line up. Now I take it outside of the magnetic field, or I take the external magnetic field away, and this piece of iron attracts iron filings and small nails. It's a magnet. But now suppose I'm careless with this piece of iron and I drop it a couple of times, that is outside a magnetic field, outside an external magnetic field, and I find that it loses its magnetism. The reason for that is because the domains have become scrambled again. That could also happen again as if I heated it up too much and the thermal motion scrambles the domains. So that explains why not all pieces of iron or other metals are magnets, because they have to have the domains aligned as well, and the domains can become misaligned if you drop them or do other things to them. But what about another phenomenon which is called magnetic induction? Because although every piece of iron is not a magnet, every piece of iron, or again pretty much every piece of iron, can be picked up by a magnet. So if I have a bar magnet and I can pick up nails with it, the nails themselves are not magnetic. I can't use the nails to pick up another nail. However, I can always pick up the nails using the magnet. But I can't pick up my hamburger or, water using the magnet. I can't pick up other materials. I can't pick up grass using the magnet. I can only pick up metal things. So what is it about iron that allows it to be picked up, that is attracted by a magnet, even though it itself is not magnetic? And this is the phenomenon we refer to as magnetic induction. Basically because, remember, the problem with the let's talk about the iron nails. The problem with the nails is that the domains inside the iron are all scrambled, and so the spins are cancelling each other out, so there's no net magnetic field. If I now take my bar magnet and move it next to the nail, then that externally applied magnetic field exerts a force on all of the electrons, or many of the electrons inside the nail, thereby causing the domains to all line up. Therefore, it now is acting as a magnet essentially, and so it will be attracted to my bar magnet. This is essentially the same thing that happens if I take a charged object, an electrically charged object, going just back to the world of electricity here, and move it near a neutral object. It will induce a charge by pushing away the opposite charge. By pushing away like charges and attracting unlike charges. It induces a charge in the other object, and thereby can attract it, even if this other object was initially neutral. So it's the same thing with magnetic induction. As long as the material can be magnetized, if I move a strong enough magnet near it, it will magnetize the material and then they'll attract. But if I then move my bar magnet away, probably my metal nail here won't be magnetized anymore, because it was only originally magnetized by moving my bar magnet near it. Again, I've said that you can align the domains in say, an iron nail if you heat it up a little bit, or strike it, or rub it with the bar magnet. You just sort of have to mechanically manipulate it so that the domains line up. And in that case, you can make the nail magnetic, and indeed people have probably done this in science class before, so you can make it so that the nail attracts other nails. But if you don't deliberately do that, then when you remove the bar magnet, the nail won't be a magnet anymore, because the domains only aligned temporarily when the external magnetic field was applied. But if I then try and use my bar magnet to pick up a piece of grass, grass is not a ferromagnet. So it doesn't have those aligned atomic spins, even within its domains. I mean, grass doesn't really have magnetic domains, but it doesn't have aligned spins at all. In other words, you can think about every lump of iron or every ferromagnet as a magnet waiting to happen. It's waiting for its domains to be aligned so that it can become a magnet, in a sense, obviously. But grass and other things, most of the materials are not like that. They're not even potential magnets, because they don't have aligned atomic spins in this way. So that means you can't induce them to become a magnet. You can't attract them using a ferromagnet, because there's nothing to align there. It's not like its domains were just waiting to be aligned and then it would attract to the bar magnet like the nails were. The grass isn't like that at all. The atomic spins are not aligned with each other at all, or possibly it doesn't have unpaired electrons. One or both of those things fails, and so you can't induce a magnetic field in the grass or other materials. So that hopefully explains the difference between non-magnetic materials, grass and plastic and most things, and ferromagnetic materials, which you can attract using magnets, but are not magnetic themselves. So that's like your refrigerator when you stick the magnet on it, or iron nails, or whatever else, and actually magnetic materials like your bar magnet or your electromagnet. So what matters is whether it has unpaired electrons, whether those unpaired electrons are able to align with each other within a domain, within a magnetic domain, and thirdly, whether those magnetic domains themselves are all aligned with each other. Only when you get those three things being met do you get an actual magnet. If any one of them fails, then you will not have a magnet. And materials that are not ferromagnets are called either paramagnetic, which means that they're weakly attracted by magnetic fields, but it's not a very strong field, and you can't make them to be a permanent magnet. Many metals are paramagnetic, so that's why you maybe, if you have a piece of metal that's not iron, it's some other metal, you might be able to sort of weakly attract it using an iron magnet, but the attraction is not very strong, and you can't turn this other piece of metal into a magnet itself. So those are paramagnets. Diamagnetic materials are most things, organic materials and plastics and water and so on. Either they don't have any unpaired electrons, or what unpaired electrons they do have can't align with the spins can't align with each other, so they are not attracted by magnetic fields at all. So just to recap, diamagnetic basically means it's not magnetic. Paramagnetic means it's a little bit magnetic, but can't be a magnet itself. Maybe it can be a little bit attracted by a magnet, but it can't become one. Ferromagnetic means that it might be a magnet as long as its domains are aligned. Okay, so that's magnetic materials and where the magnetic field actually comes from. Now, to conclude, let's have a look at some applications of electromagnetism. So, electric motors and generators. It turns out these are actually almost the same thing. To understand how an electric generator works, we need to understand the concept of magnetic flux. So let me explain that briefly. Imagine that I have a loop of wire, just a circular loop of wire. Now imagine that I have, just think of my fingers. I'm pushing my fingers through the wire so that the wire is around the fingers. It's like I'm wearing a bracelet, except instead of around my wrist, it's around my fingers for some reason. That's how I'm poking my fingers through the wire. The loop of wire. It's going through the loop, okay? But now forget about my fingers. Instead, imagine that I'm pointing magnetic field lines through the loop of wire like that. Okay? Hopefully you can visualize what I'm talking about here. It's just a loop of wire with magnetic field lines poking through. that is magnetic flux, basically. Or more specifically, the magnetic flux depends on how many of those magnetic field lines are passing through the circular loop of wire. Also, how big the loop of wire is. So the bigger the loop is, the bigger the magnetic flux is. And also the strength of the magnetic field. So the longer are those arrows, those vectors that are pointing through the loop. The longer those vectors are, then the stronger the magnetic field is, and so therefore the bigger the flux is. And also the orientation matters. So it turns out that to contribute to magnetic flux, the vectors, that the magnetic field must be pointing perpendicular to the wire. That is, it must be poking through the wire. It can't be sort of diagonal or on the side, because in that case it won't contribute to the magnetic flux. This is similar to the Lorentz force law that I talked about earlier, where the proton had to be moving perpendicular to the magnetic field. It couldn't be moving parallel to it, because that wouldn't lead to any force. So same thing here. Magnetic flux is just proportional to the number of magnetic field lines, and also the strength of those field lines, passing perpendicularly through a surface, or you can think about it as through a coil of wire. There doesn't actually have to be a wire there, but that's a good way of thinking about it. Now, why would we care about this? Well, because it turns out that the bigger the magnetic flux is, the larger is the electric current that's induced in the wire. Or, let me be a little bit more careful, because it's not the magnetic flux itself that produces an electric field, and therefore an electric current. If you remember the relationship I talked about between electromagnetism, between electricity and magnetism, a changing magnetic field produces a constant electric field, which means that a changing magnetic field also produces an electric current, because an electric field will lead to an electric current if there are charged particles to be moved. Another way of saying that is that a changing magnetic flux, a change in the number of these vectors pointing through the wire, a change in that will produce a current in that wire. Now, why on earth would I care about something so strange and esoteric? Well, because that's exactly how electricity is generated. All you have to do to generate electricity, that is to get a current to flow in a wire, is, well, get a wire and pass magnetic field lines through the wire, pointing up like my fingers were pointing through the loop. And then somehow, so that's magnetic flux, the magnetic field lines that are pointing perpendicularly through the loop. That's magnetic flux. Now all I have to do to get a current is somehow change that magnetic flux and keep it changing. Obviously, if it changes for a fraction of a second, I'll get a fraction of a second of current, and then the current will stop. I need to keep changing that magnetic flux in order to continually have a current running through that circuit. And then I can use that electric current to do whatever I like, to charge a battery or to run my computer or whatever. Okay, but how do we get the magnetic flux to continuously change like that? Well, there's a number of ways you could do it, but the easiest way is just to rotate that loop of wire. Because as it rotates around, imagine that as it's rotating around, it's changing the angle between the loop of wire and the magnetic field lines. Eventually, instead of the magnetic field lines passing through the loop of wire, they'll pass alongside, so that, for example, that instead of the magnetic field line pointing up through the middle of the loop of wire, it's now pointing up, and it passes through one side of the wire, and then it passes through the empty space in the middle, and then it passes through the other side. So, if you think about the wire as a ring, instead of going through the hole in the middle of the ring, it's actually hitting one side of the ring and then passing it through the middle space and then passing out the other side. It's moving radially with respect to the loop instead of through the middle. Hopefully you can sort of visualize what I'm saying there. As I rotate the loop around, that is the loop of wire around, the number of field lines and their angle with respect to the loop of wire will change. They'll reach a maximum when the field lines are perpendicular to the loop of current. So that's when the magnetic flux is biggest, and the magnetic flux will be smallest, actually it will be zero, when the loop of wire is parallel to the magnetic field lines. So that continual change in the magnetic flux will produce a constant. If I keep the rate of change of magnetic flux the same, that will produce a constant electric current. Electric field, therefore electric current, that will keep flowing through the wire. Well, when I say constant, the electric current will be constant in terms of its maximum amplitude, but the electric current will vary, of course, depending on how rapidly. It will vary just as the magnetic flux varies. So I should clarify that. The current is sinusoidal, which is what we call alternating current. The voltage is continually going up and down, but the maximum magnitude of that current will be constant if I'm continually rotating the piece of wire at the same rate. So anyway, all I have to reiterate, all I have to do to generate an electric current is get a magnet, put a loop of wire inside the magnetic field generated by that magnet, and rotate it around. And then a current will flow through the wire. Okay, then, well, how do I rotate the loop of wire? I mean, I could just stand there turning it around, but that's sort of slow and very boring. In practice, the way we do it is we use electric generators. So we turn it by producing some, by using some force. Usually, it's either falling water, which is what hydroelectric dams do. Literally, falling water pushes turbines, which then turn the loops of wire inside magnets, which then lead to a change in flux, which produces an electric field, which then leads to electric current flowing through the wire, and then we get electricity. That's hydroelectric dams. Coal and oil power and many other types of geothermal as well all use rising steam or steam pressure, but it's the same basic idea. The steam pushes the turbines, which turn the loops of wire placed inside magnetic fields. That change in magnetic flux produces an electric field, which in turn leads to an electric current flowing through the wire, and again we've got electricity. So pretty much all power generation, electric power generation, relies on this principle of you turn a turbine which rotates a wire inside a magnetic field, which produces an electric field, which then produces electric current. The only exception that I know to this is photovoltaic cells, which operate quite differently. They don't use this principle, but pretty much everything else does. So that's pretty amazing. We've got an electric generator just by turning a loop of wire inside a magnetic field. But we can actually go further than that. Imagine running the thing in reverse. Instead of putting motion in the form of continually rotating the electric wire, and that's where the energies ultimately come from. The energy's not actually extracted from the magnet, because the magnet isn't used up or anything. The energy's coming from the continual rotation, the mechanical energy I have to put in to keep rotating the wire. This whole setup is just a way of changing that mechanical energy into electrical energy flowing through the wires. So that's where the energy is ultimately coming from. But imagine, instead of putting mechanical energy in and getting electrical energy out in the form of the current, what if I ran it in reverse? What if I put electrical energy in and got mechanical energy out? That would then, if I did that, that would be called an electric motor. And in fact, that's exactly how electric motors work. It's just a generator running in reverse. That instead of turning the wire and producing a current, you run a wire through a loop, which when placed in a magnetic field will cause the loop to turn, thereby turning a generator, or which can turn a crankshaft or do whatever other mechanical work you like. But the point is, it works in both directions. It just depends what type of energy you're putting in and what type you want to be taken out. So that's really all there is to it. Obviously, the precise engineering of the details of how these work is very much more complicated than the way I've described it, because we've been building these things for quite some time now, and they've got quite sophisticated to increase efficiencies and so on. But fundamentally, that's all that it is. It's wires turning in magnetic fields. If you put in the mechanical energy and take out the electrical energy, then what you've got is an electric generator. If you put in the electrical energy and take out the mechanical energy, what you've got is an electric motor. Now, finally, let me just finish by mentioning Maxwell's equations. An episode on magnetism would certainly be incomplete without mentioning those. Maxwell's equations are a set of 4, sometimes a fifth's included, but I'll say 4 partial differential equations. Don't worry if you don't know what those are, just think of them as mathematical equations, which essentially completely describe classical electrodynamics. So these were developed in the late 19th century, so they don't include like quantum mechanical stuff. But apart from that, so ignoring the quantum side of things and the special relativity side, Maxwell's equations completely describe classical electromagnetism. That is, if you just had these 4 equations, well, sort of plus the Lorentz force law, which is sort of the lonely fifth one that's sometimes tacked on, if you just had these 5 equations, that is in principle enough to explain any electric phenomenon. So anything that's happening inside your computer or your television or any electric device that you have is in principle explainable just by using those 5 equations. I say in principle because in practice it's an awful lot more complicated than that, and in practice the equations are not actually often very useful for calculation, and you need to have other approximations and other tools to use. And it's also the case that quantum effects are becoming more important in electronic devices these days, and you can't explain those using Maxwell's equations. But, subject to a few caveats there. Basically, Maxwell's equations themselves are enough to explain the entire force of classical electromagnetism, which is why they're such a huge thing, which is why they're seen as a really big achievement in physics. So what are these 4 equations? They're quite short and simple equations, really. There's Gauss's law and Gauss's law for magnetism. They're the first 2. They're quite easy to understand. Gauss's law just says that a static electric field points away from positive charges and towards negative charges. And that's really what it says. So Gauss's law for magnetism says that magnetic fields point away from north poles and towards south poles, and it also says that there are no magnetic monopoles. So basically, Gauss's law and Gauss's law for magnetism Gauss's law describes static electric fields, and Gauss's law for magnetism describes static magnetic fields. So they mirror each other. Now, if you look at the mathematics behind these equations, you'll wonder how on earth I translate Gauss's law for magnetism into what I just said in words. But obviously, I won't be able to describe the mathematics behind it in the podcast. But conceptually, I'm giving you an idea as to what the equations say. So those are the first two, Gauss's law and Gauss's law for magnetism. The last two are called Faraday's law and Ampere's law. Faraday's law states, and hopefully this should sound fairly familiar, it states that the strength of an electric field passing through a loop, like a loop of wire, is proportional to the rate of change of the magnetic flux through the surface of that loop. Hey, that's exactly the principle that I just explained for how electric generators and motors work. So they work by using Faraday's law of induction. Ampere's law is pretty much exactly the reverse. It states that the strength of the magnetic field passing through a loop is proportional to the rate of change of the electric flux passing through the surface, plus the amount of electric current flowing through the loop. So, don't worry if you haven't got all the intricacies of that. But basically, Faraday's law and Ampere's law taken together just say the thing that I said way earlier in the podcast, which is that a changing electric field produces a magnetic field, and a changing magnetic field produces an electric field. That's what Faraday's law and Ampere's law say, essentially. So Faraday's law and Ampere's law describe changing electric and magnetic fields and how they relate to each other. Gauss's law and Gauss's law for magnetism describe static electric fields and magnetic fields respectively. And Gauss's law for magnetism, as I said, has an extra element in it whereby it says that magnetic monopoles don't exist. If you look at Gauss's law for magnetism, it says stuff equals zero, basically, and that zero is how it says that there are no magnetic monopoles. Because essentially what it's saying is that with any given volume of space, there's always a north pole pointing in one way and a south pole pointing out the other way, essentially. And so they always cancel out to zero. Whereas that doesn't happen for electricity. For electricity, if I shrink my volume of space enough, I can just isolate a single positive charge, and so that the charge there is not necessarily zero. It can be positive or negative. But you can't do that for magnetism. That's what Gauss's law of magnetism says. It's for, regardless of how big or small you take your circle, you've always got a net zero amount of magnetic charge, essentially. That's one way of thinking about it. Anyway, that's all for this episode. I hope it was somewhat clear. It's a little bit tricky to try and explain electric magnetic fields and vector perpendicularities and such things without the benefit of diagrams, but I will post some of those up on the Facebook page, so check that out if you're desirous for some more. Also, please log on to iTunes and give the podcast a favorable review or a rating. It really does a lot to help boost the visibility of the podcast and hopefully attract more listeners who would benefit from learning some science. So if you like learning science and would like to help other people learn more about science too, then jump onto iTunes and do that. Also, I'd appreciate it if you would have any feedback about the podcast, things you like, things you don't like, topics you'd like to hear. Send me an email. My address is fods12@gmail.com. That's FODS12@gmail.com. So thank you for listening. I'll talk to you next time. Just a short postscript. In editing this podcast, it came to my attention that when I was describing the direction of motion of a positive charge, that is a proton, in a magnetic field, I got the direction wrong because I was using the wrong form of the right-hand rule. So it turns out that if you have a magnetic field that's facing away from you and a positive charge moving to the left, that means that if you hold your palm flat, so your fingers are pointing forwards away from you in the direction of the magnetic field, extend your thumb to the left, because that's the direction that the positive charge is moving in. So your palm should be facing down. So that tells you that the force on the charged particle is acting downwards, not upwards, as I said. So that's a minor error. It doesn't change qualitatively anything that I was saying, but just a note to any astute listeners who picked that up.